This talk is more about uh, building the systems that power the experience of before a user hits play on the Netflix streaming service. And so things like title metadata, like summaries, ratings, synopsis, whether or not a title is licensed to play in a country, or things like recommendations, which list of titles to show to a user, in what order to show them. These data access patterns share a common paradigm, and services that power these are not looking up in a database or a cache fronting of database. These services at Netflix are dominantly powered by this paradigm called versioned caching. I'm Sunjeet, and I work on the caching team.
Hello, I'm William. I work on the online data stores team for our key value store.
So a lot of people in this room might be familiar with demand-filled caching. It's a popular pattern. And a quick level set, demand-filled caching is the dominant pattern in our industry. It is the right answer for a huge swath of workloads, and we even run it at scale within Netflix. It powers around 500 million operations per second. And some of the use cases that demand-filled caching powers at Netflix is things like IPC response caching, Spring method result caching, behind the key value abstraction, and other abstractions like distributed counters and graph and time series, and the EV cache offering within Netflix itself. And so this talk is about focusing more on a more prevalent pattern than demand-filled caching at Netflix. And just to illustrate the usage of these patterns, if we map all our caching use cases by count and data volume within Netflix, version caching pattern dominates. So on the left, in the gigabyte scale, you have hollow and raw hollow, which serve hundreds of use cases entirely in memory and versioned. And on the right is the terabyte to petabyte scale, where we have an architecture called UDEM and the largest action-style EV cache deployments at Netflix, which are also versioned, but data is hosted remotely. So two of the three regions are versioned, the one with the most use cases and the one with the largest data sets. And so what is a version cache? There's three key properties of how we define a version cache. Uh, One, data is published as snapshots and deltas are applied between versions. Two, there's an atomic cutover on consumers from a version n to version n+1 in a single operation. So there's no reads that span the boundaries of those two versions. And finally, within a version, data is immutable. That's all. And so a fundamental distinction between demand-filled and version caching could also be made as demand-filled is more reactive to a user's request, whereas version caches are more proactively staging the data for the time of query. And we'll take a look at how these version caches help Netflix. In short, they sidestep some of the toughest problems in caching that apply to demand-filled caches, like cold starts and misfilled thundering herds. They offer an operational simplicity, and they provide organization leverage by helping engineering teams evolve their data access patterns without coordinating with each other. We'll take a look at the four caching architectures along these four dimensions by data footprint. How big is the data set from gigabytes to petabyte scale? Consistency, how stale can a data set be? And that could range from milliseconds to hours depending on use case. Latency, nanoseconds in process to microseconds for Memcached or milliseconds for Cassandra, and cost from local RAM to remote disk. For each architecture we'll cover, it lives in a different region of the space for these four parameters. And here's the map. So hollow and raw hollow share the same tiny footprint, about 10 gigs of compressed data set, but different consistency profiles. Raw hollow gives us near zero staleness, making the cache also being capable of a source of truth. EV cache lives in the microsecond latency band, whereas UDEM is in the millisecond petabyte minutes to hours of staleness corner. Next, let's look at each one of these a bit closer. Let's start with the two architectures for smaller datasets, where our version datasets offerings are more mature, and starting with Hollow. Hollow is Netflix's open source versioned cache for small to mid-sized datasets. Many content-related datasets, like the catalog of all videos, are hosted in Hollow. It has four key properties. It's a near cache, so data lives on heap in the client's JVM. It's total, so every consumer holds the entire data set. It's immutable, that as in once published, a version of a data set doesn't change. The consumers get a read-only view of the data set, and it's eventually consistent. So propagation delay is in seconds to minutes. But its usage numbers within Netflix are staggering, and a lot of the content-related data sets are mastered in Hollow, but also some of the other Open Connect data sets in other orgs, like config is another common example. Altogether, these data sets support around 1 billion requests per second and are deployed to 100,000 EC2 instances and used by about 75 engineering teams within Netflix. But the cost of infrastructure of maintaining the Hollow offering is a bit under $5 million a year of infrastructure. So at a low cost, it provides a lot of leverage. And since the entire data set is in memory, reads are nanosecond latency. There's no syscalls or no I/O, no network calls in serving these reads. But one might wonder, how big can these data sets be to fit entirely in memory? Well, the answer is more than what we might expect. Hollow is able to achieve orders of magnitude compression by using deduplication and ordinal references and bit packing. So, so a couple of examples are an identities data set, which when modeled in Neptune DB was around 20 terabytes, and modeled as Hollow was a bit under half a gigs. And another core movie metadata, which is around hundreds of gigs when represented in JSON, is a bit less than a gig when represented in Hollow. It's been in production for over a decade, and how it works is producer apps compute snapshots and deltas that are encoded as Hollow blobs from upstream sources of truth via scan, incremental updates, or transforms. And these blobs are published to some durable central storage we couple with Amazon S3. Consumers subscribe to updates and pull down these published snapshot or delta blobs and apply them atomically, locally, and they get a read-only view into the data. The consumer business logic always sees a fully referential, consistent view of the entire data set and never a partial state. And data is organized columnar and supports schema evolution. And because the data set is entirely memory on the consumer, it can be indexed locally and queried in any which way the consumer app needs to based on its requirements and at in-memory performance. And it's really a very operationally simple pattern that consumer teams love to apply, because the total in-memory data fundamentally changes the game if the data sizes can afford it. There's zero read path scaling required. Reads are local in-memory lookup, so add more instances in the consumer app and you add more capacity for free. There's no data access pattern assumptions. Because the reads are just in-memory lookups, and the whole data set is on every node, any query is fast. The publisher doesn't have to design their data model around access patterns. Data models and access patterns evolve on consumer teams without coordination between the producer and consumer teams. And finally, production data quality tends to be really stable, because this version publish paradigm offers things like validators, region staggered rollouts, version pinning, history, and diffs, all possible because the data set is versioned. But Hollow consumers can only read, and the natural next question is, what if an app wants to also be able to write incrementally to these data sets? And that's where like another different abstraction over Hollow that we call read after write Hollow or raw Hollow comes in. And it's also a total in-memory version data set similar to Hollow, but mutable and with read your writes consistency. This property makes the cache offering also be capable of being a source of truth. So where traditionally an app might couple with a different database as a source of truth and also move data to Hollow to support high-scale consumer access, it simplifies that apps model to just using raw hollow as the source of truth and as the scalable cache for consumers. So there's no separate database, and it's built on top of the same hollow infrastructure. How it works is writes go to a small raw hollow cluster, which replicates them to clients immediately and compacts to snapshots periodically. While compaction is in flight, recent writes are held in a per client overlay. So reads are still in memory against a base hollow snapshot plus the local overlay on the client. If you need strong consistency on the reads, you make a remote call to raw hollow, and the consumer model is largely unchanged total in memory typed API access. The reason raw hollow is a popular pattern at Netflix is because it eliminates that database tier, and where you needed a source of truth plus a hollow producer, it's now one single system and one single dependency, which halves the tech debt and long-term operational concern. And from this new source of truth store, you can read at eventual consistency effortlessly at scale because every read is in memory for clients. Raw Hollow has become the default data store and cache for enterprise scale apps, which is about hundreds of apps at Netflix. And the data set scale is about hundreds of gigs of the entire data set uncompressed. Together, Hollow and Raw Hollow work well for small and mid-sized datasets at Netflix. But what happens when the dataset is much bigger and the whole dataset doesn't fit in memory on every client node? You still want the benefits of versioning, like atomic cutover, validators, and rollback. You just can't hold the entire dataset locally. Our first inspiration here is application level versioning built on top of EV cache, which is not a versioned cache. Some folks might be familiar. EV cache is a distributed cache built using memcached and spy memcached. And Action, which has been published on the Netflix Tech blog in the past, but Action is one EV cache cluster, and it's the largest one that we run, and it powers Netflix's recommendations by serving member-keyed ML facts in the memcached ext store. The scale for this one dataset is 8 petabytes on disk. It has about 250 billion keys, and it deploys on a 2,000 node cluster per AZ replica. An Action implements versioning on top of EV cache, but at the application level. A periodic Spark job computes facts and stores it in S3 for durability, and EV cache for low latency querying. Entries are keyed by date. Each day's data is immutable once written. Version cutover happens at the app layer, and 18 trailing days of versions are held in the cache. So you get versioning, but only as a convention layered on top of a non-versioned cache at the app level. This was an inspiration for the next architecture that William's going to talk about, where versioning is not an application level convention, but a platform default. And when versioning is laid as an application convention over a caching data store does not support versioning, two things happen. One, incident response, as we witnessed, involves multiple teams. We've had things like TTL bugs that require custom recovery. And two, versioning at the app level is hard to scale to other use cases. And so in the next architecture, William's going to talk about versioning as a first-class platform feature, not an application convention, and at petabyte scale.
Excellent, thank you. Yeah, so I'm going to talk about an architecture that we call UDOM, which stands for offline to online data movement. And as Sunjeet queued up, this is kind of inspired by the success of Hollow and the challenges of scaling the Hollow data model, the kind of version cache data model into something like EV cache without supporting versioning as a kind of first-class component. So what we're trying to do is take all the kind of successes and learnings of Hollow, of how nice it is to separate your writes from your reads, your preparation from your serving, but scale that to the data sets that don't fit in memory, that can't compress very nicely. Big machine learning data sets is a common use case, and there are many more. So the kind of core thing here is that users are interacting with specific versions that are prepared offline through large Spark jobs or other kind of big compute jobs that can consume from big pipelines and figure out a set of data that then is going to be served online later. And the key point is isolation. So what Hollow does really well is it isolates every component so that users never have to experience the cost of writes when they're doing their reads. They can just continue to consume the next version down, and they can continue to treat that version as an isolated next step up in the process of updating their data. So Udom tries to bring that same thing to kind of a database architecture. And we do it via hydrating our data stores from some source, which is generally S3. So for example, we prepare some large data set, we chop it up from whatever format it's prepared into some format that we can serve it. So either Cassandra SS tables or in another custom read-only solution into Roxyb SS tables. And then we can download those data sets into new isolated structures. So in the Cassandra case, we can download them into new levels and then atomically insert them into the LSM. Or in the partition KV case, we actually can download those data sets onto completely fresh infrastructure. So we can isolate at the EC2 level and say, we're going to spin up a new ASG. We can spin the compute on this ASG and maximize the throughput of downloading these data sets to potentially move huge data sets, petabyte data sets very quickly, or at least as quickly as we can, without ever affecting the read performance. And we can hide all of this placement information behind our key value API. So users can both choose between these two models, they can layer these two models. I'll give one example. A popular model is to have a kind of a large immutable set mixed with a small mutable set, which is kept in Cassandra, and to hide the merge of the two behind the key value layer. That's an architecture we're exploring more and more. And so what does this buy us? We now have the kind of scale of these large data sets, but we have the semantics of Hollow and of version caching in general. So first of all, this is a very familiar semantic to developers, especially at Netflix because we have Hollow, but just in general, people are used to working with data updates that feel like deploys. We're used to deploying our code, rolling back our code, validating our code through canaries. All of this is now possible also at the database layer. You can spin up effectively a new version of your database, canary traffic to that, run arbitrary validation against it with no effect on your production infrastructure, and only when you're ready can you cut over. It also is much cheaper and faster to deliver this bulk data. The isolation allows you to kind of focus on serving the new update without worrying about affecting production traffic. So you can be much more aggressive in kind of the scale and scope of that new delivery. Yeah, so that's Udom. I'll hand it back to Sunjeet to kind of summarize what version caching gives us and finish things off.
So just zooming out back into version caching in general, this paradigm gives us no cache misses triggered through thundering herds. So if you've operated a demand-filled cache, you might be familiar with some of these caching problems, which can not be solved, but only be sidestepped. You don't need to be worried about cache invalidation or referential inconsistencies with the source of truth, since new versions replace old ones atomically. There's no cold start problem because consumers bootstrap from the latest snapshot. Referential integrity is intrinsic. You never see a partial state of the data set. Data validation is straightforward because every version is a discrete, addressable artifact that can be validated independently. Pinning is a very useful one operationally, where any consumer can be held at a past version of the dataset where other consumers can see the latest versions. Or history, so it's possible to diff between any two versions of the dataset or see a diff, like an audit trail of a dataset, of changes to a dataset over time. So most of these are problems that demand-filled caches have to solve at runtime, often imperfectly, and version caches help sidestep them entirely. But only if the use cases allow for it. So it doesn't come for free. The trade-offs are propagation delay is a big one. So if the use cases allow for seconds to minutes to hours between a producer writes and when a consumer needs to see those writes. But if you need real-time mutable record level access at high throughput, then this is not your paradigm. And producer complexity and system complexity are like for building things like version coordination and snapshot bootstrapping are real costs too, but engineerable. So consider version caches when you have a high number of reads and they greatly exceed writes, and you need to serve these reads at high availability. But consider alternatives when every write must be immediately visible, and data is highly user specific or rapidly changing. That's it for our presentation. Happy to take questions or stick around after. Thank you.